research achievement. So the second distinguished advisory board member is Professor Leszek Wojtkowski. So he is from the Polish Academy of Science in Poland. And the third one is Professor Marek Pawełczyk. So he is from CBCN University of Technology in Poland. So welcome. All of these are new distinguished advisory board member, and I hope we could use their advice and also their great experience in the science and also the technology, and would be definitely helpful for our journal to be developed in a very good way in this society. And I personally thanks these three distinguished board members. And today we learn more from Professor Jiang in his speech today. So the journal since 2021, so you see that in the first volume, we published 10 articles. In the second volume, in the 4 issues, we published 18 articles. And in the third volume, we published 9 articles. In total, 37 articles has been published. So thanks to our journal office, and also the managing editor, so they help us a lot basically to look at the publication, the quality, and also with the good visibility. And therefore, this webinar today would be helpful for us to promote the publication or the publish in the complex engineering system and to be announced in the wider range. So if you are interested, so you are very welcome to look at the webpage of the journal and to look at the article has been published. And I hope these articles would be helpful for your research and then try to basically disseminate what kind of result has been published in this journal so far. And we try to basically, in the next 2 issues is left for the volume 3. So we are publishing more articles this year. And we are planning, so basically after publishing the high quality articles, try to the journal will the progress and develop much better and try to be basically indexed in more databases, and this would be also gives more advantage, the benefits to the authors of these articles. So now it's time to introduce our distinguished advisory board member is Professor Jiang Zhibin. So Professor Jiang is now a distinguished professor at the Department of Management Science, the Untitled College of Economics and Management, and the Dean of the Sino-US Global Logistics Institute, Shanghai, Japan University. So Professor Jiang is the Changchang Scholar, Program Chair, Professor of the Ministry MOE China, and also a Fellow of Institute of Industrial and System Engineering. So Professor Jiang is the Vice President of the Chinese Industrial Engineering Society, Vice President of the Advisory Committee of IE Undergraduate Program of MOE China, and the former Regional VP Vice President of IISE for Asia 2019-2022. So he has long been engaged in research on discrete dynamic event system, operation research, based modeling, and control theory methodologies for complex production operation management. Professor Jiang finished or is undertaking 3 NSFC funded projects, 8 NSFC funded projects, and over 20 other China national projects. So I'm very pleased to introduce Professor Jiang to the community, and thanks a lot to him for accepting our invitation to give this speech to this webinar platform for more audiences. I hope the audiences today, so they would be also the basic after finishing the Professor Jiang presentation. If any question arises, please communicate with us through this chat box, or you can ask your question directly from Professor Jiang. So the topic for today is about optimal decision making in complex supply chain networks under the make-to-order manufacturing paradigm. So because of time, I can stop my presentation at this stage. And again, thank you again for joining the webinar today. And please consider the Journal of Complex Engineering System for your future the publication of your result, and please help to promote the journal in your network as much as possible. Thanks again to all of you. And now I can ask my good friend and also my good colleague, Professor Jiang. Professor Jiang, so the floor is yours, and please, you can, if you're ready, please, you can start your presentation. Thank you very much.
Hello, everyone. Good evening. So I'm very pleased to have this speech online. So and also thank you, Professor Karmi's invitation. So invite me to join the advisory board for this very good journal. So I'd like to have this talk from the for my recent research progress. So far, you know, the hot topic for the manufacturing is intelligent manufacturing. So I have been researching on a key NSFC funded project for operation management for intelligent manufacturing. So today's topic for my is on optimal decision making for complex supply chain network and make-to-order manufacturing paradigm. So you know, under this. So my topic is includes the following six parts. So starting with introduction. So you know, in the context of Industry 4.0, the manufacturing section is moving from automation towards intelligence. Many countries around the world have put forward their country's agendas or strategy to revitalize manufacturing by taking intelligent manufacturing as important grips, such as Advanced Manufacturing Partnership Program proposed in 2011 by United States, Industry 4.0 development strategy proposed by Germany in 2011, Made in China 2025 plan proposed by China in 2015 and other countries. And the intelligent manufacturing system will changing manner how information interact and work is done, thus changing the way of production and the operation is managed. As a result, manufacturing systems become much more complex. Empowered by the key technology associated with Industry 4.0 as autonomous robot, simulation, and the Internet of Things, intelligent manufacturing systems have the characteristics of the integration, flexibility, networking, and being autonomous. These characteristics help intelligent manufacturing systems take advantages new generation of information and communication technology to adapt to the changes in the internal and external environment of the process and make a more rational operation management decision. However, in order to realize and match these features, production and operation management method needs to be changed as well. We have to face the great challenges of intelligent manufacturing phase in multidimensional integration of network supply chain within and across plant, and the network production with shared resource across multiple plants. Traditional sequential production, inventory, and delivery scheduling does not match these features of intelligent manufacturing, and thus need to be innovated. Especially, some enterprises are adopting integrated planning and scheduling approach to coordinate production, inventory, and delivery to realize quick response to customer at a minimal cost. However, integration, planning, and scheduling face many difficulties, such as the complex structure of the supply chain network, the many decision variables and constraints, and the complex objectives, which will show in my following topic, and the lead in considering this coupling between production, inventory, and the logistic decision in the supply chain network. Therefore, the scale and complexity of this integrated optimization problem is of large scale and large difficult to resolve. With this progress in the economic globalization in the recent years, supply chain has evolved from a chain to business with one-to-one, business-to-business relationship to complex network of business and relationships. Simply speaking, a complex supply chain network is a complex dynamic systems that connect the suppliers, manufacturers, distributors, and customers, in which the members are closely interrelated and interact in a complicated way. Suppliers, manufacturers, distributors, retailers, customers, and other components in a complex supply chain network can be abstracted as a load with heterogeneous behaviors. The typical structure of the complex supply chain network can be illustrated in the figure, in which there are complicated relationships of flows and connection, that is, material flow, information flow, contract flow, and financial flow among all kinds of partners. Hence, manufacturers in the complex supply chain network must have the ability to make collaborative management decisions to improve performance and adapt to the complex supply chain network. Against the previous large demand for fewer products and multiplying products choice, customer demand have progressively been geared toward personalization and diversification. To satisfy personalized demand, manufacturers have increasingly changed its production paradigms from make to stock for mass production to make to order production, ranging across sections such as customized furniture, fashion apparel, steel, food and catering service, and electronic products. Advantages of MTO paradigm includes matching customized demand effectively, reducing warehousing and inventory costs, providing more differentiated products, and achieving better customer services. However, MTO manufacturers are weak in longer lead time and higher cost, since it cannot meet customer demand through inventory. Instead, it can only produce by a single piece or small batch product after receiving orders. To remain competitively in the market, manufacturers must shorten lead time to rapidly respond to demand while considering product quality and cost. Thus, it is critical for manufacturers to plan and schedule the production and the delivery of product quickly and cost effectively. With the continuous development of Industry 4.0, numerous manufacturers establish multiple plants for cooperative production across locations, either within low cost, low level, and raw material cost, or in proximate to customers. Multi-product network production offers the advantage of quick response, no cost, and high flexibility and resilience. It has extensive application in a wide variety of industries, such as furniture, fashion apparel, steel toys, and high-tech products just mentioned. Plants that distribute in different locations are usually heterogeneous with different capacities, processing time, production, and inventory cost and locations. Supported by NSFC, we have been investigating a key project on operation and operation management in the intelligent manufacturing. This study, to be shown in this talk, is motivated by applying innovative decision-making approaches to a manufacturer of customized furniture that collaborates with us. This manufacturer produces and sells several types of products under MTO paradigm, including wardrobes, cabinets, doors, and beds, all of which are tailored to customer needs, such as preference for style, color, size, and so forth. Each customized order consists of one or multiple different types of products we referred to as job in the following talk, with generalized size. In other words, walls are splitable to different jobs or products. Upon receiving customized order, the manufacturer should assign job to heterogeneous plants, and various types of job contained in one order may be produced by more than one heterogeneous plant at different times. The manufacturing system for the company is regarded as a complex supply chain network, including multi-location heterogeneous plants, distribution center, and customers. A distribution center are scattered far away from each other across the country. Each customer comes to the nearby distribution center to place his or her order and define requirement at the beginning of the planning horizon. Then each DC makes personalized designs for the jobs contained in the order received and forward the different jobs to different manufacturers. The manufacturer needs to organize production of multiple products by assigning job to plants and setting a day to start production for each job. Moreover, the manufacturer should also make a decision on delivery of completed jobs to their customers in two stages in a hub spoke. We also refer to as a pull point delivery network. The hub spoke delivery network contains a set of separate hubs, that is a distribution center, and a set of spokes that act as a link between hubs and the nearby demand point. In the first stage of the delivery, completed products are transported from plant to the distribution centers. In the second stage, the manufacturer delivers all the ordered product to the customer at the same time. Product delivery is completed by a third-party logistics provider. They dispatch their vehicles to plants or distribution center to pick up the job or order ready for the transport at the end of each day. And the completed job may be stored temporarily in the warehouse of the plant or distribution center if necessary, which may incur additional holding cost. Manufacturer needs to make a decision on the delivery in the terms of dispatch time from a plan for each job and determine delivery time for each order. So as we just described, the manufacturer should simultaneously make decisions both on the job production at different plant and also finish the product delivery in 2 stages, which is integrated production and delivery schedule problem. That is IPDS for short. This IPDS problem is characterized by several complicated features. First, diversified job to be finished at plant network composed heterogeneous plant at different locations. Secondly, the 2-stage delivery of finished job in the hub-spoke delivery network, where transportation time and the cost vary depending on the plants and the distribution. Certainly, finished job may be stored temporarily in the warehouse of the plant or distribution center, where different inventory costs are incurred. Finally, each order compromises one or multiple jobs, each of which may be assigned to different plants for collaborative production. Whereas all jobs in one order must be delivered to its customer together. Such features exacerbate the complexity of the IDPS problem. This IDPS problem also exists in other industries, such as in customized fashion apparel, steel industry, customized household appliances, and picked-to-order organic vegetables. Despite the rapidly growing interest in the IPDS, to our knowledge, no existing study have holistically considered the IDS problem with splitable orders comprising multiple jobs, which are produced in multiple heterogeneous plants and then transported in the hub-spoke network and finally delivered together to the customers. So second, literature review. Okay. So, and in recent years, the IPDS problem have attracted much attention in the last 3 decades. One stream of research consider a single plant IPDS problem with one machine or several parallel machines. Many studies address single machine IPDS problem that determine the production starting time or processing sequence and the transportation departure time for orders. In terms of the performance measure, some papers consider only delivery in timelines. Other studies focus on only minimize the transportation cost. Few existing IDS problems consider inventory in their objectives. However, none of these above studies consider the decision to assign orders to plant in the multiple plant IPDS problem and the resulting production cost difference. Some papers consider the IPDS problem with parallel machines in a single plant. Compared to the single machine problem, the decision included assigning job orders to machines and novelty, since parallel machines are homogeneous and located in a single plant, the above problems are simpler than IPDS problem for heterogeneous plants at various locations. The other stream of research focuses on the multiple plant IPDS problem, whose decision included assigning order to plants. Novelty, only a handful of papers consider such a problem, and they are all restricted to only long splitable orders. Their scheduling of production and delivery between various plant slots affect each other after order are assigned to the plant. Thus, they cannot address the difficulties inherent to multiple collaborative production for splitable orders. Furthermore, the above studies are all focused on one-stage delivery, on which each complicated job will be transported directly from the plant to its customer. None of them consider hub-spoke delivery, which is also common in many practical settings. To our best knowledge, only Jesmer, etc., and Tang, etc., studied the IPDS problem involving hub-spoke delivery. However, both these problems concerned only one type of non-splitable order produced by a single plant. To our knowledge, our paper, our talk, our work to be present in this talk is the first to investigate the practical and complex IPDS problem with splitable orders, multiple plant collaborative production, and hub-spoke delivery. In conclusion, our study differs from above Prof's work in the following aspect. First, each order is splitable, and multiple constituted jobs in the same order may be produced by various plants with different capability, capacity, processing time, production and inventory cost, and location. Second, the first stage delivery is splitable, but the second stage delivery is non-splitable in each order, can be dispatched only if all its constituted jobs have arrived at the distribution center. Next, we present the problem description and model formulation. So, I will present the parameters of the IPDS problem. So, we consider a manufacturer can produce J types of job through its production network with plant in various locations. Here, BJK is a capability parameter that equals 1 if plant K can produce type J job, and 0 otherwise. Each plant K has a daily production capability AJK and the unit production cost CPJK for the type J job with processing time PTJK. At the beginning of the planning horizon, the manufacturer receives a set of I customized order from the L distribution center, and the EIJ equal 1 if order I is from DC distribution center L and 0 otherwise. Each customized order consists of JI type of job. Type J job of order I denote as job IJ with personalized size ZIJ. Transportation of job from plant K to distribution center L with the unit of transportation cost CTKL and the transportation time TTKL. The unit inventory cost of plant K and the distribution center LI are CIPK and CID L. Each order delivered to its customer later than the committed delivery date will incur a daily tardiness cost CD. So next, I will present the decision variable of the IP problem. The decision variable comprise multi-plant production scheduling decision, including assign job to plant and determine production starting time for job, and the two-stage delivery scheduling decision, including determine departure time from plant for job after it is finished, and determine delivery time for jobs, for orders. First, we formulate the IPDS problem as a mixed integrated programming problem, MIP model. Here, expression 1 minimizes the total cost. The first 3 items denote production cost, transportation cost, and tardiness cost. The first and the fifth terms denote holding inventory cost at the manufacturing plant and distribution center respectively. Constraint 2 and 3 ensure that type J job are assigned to only one plant capable of produce this type of job. Constraint 4 ensures that if job ij is not assigned to plant K, then variable TSIJK equals 0. Constraint 5 calculate the production completion time of job IK at plant K. And constraint 6 indicates that equal 1 if only if job ij is being produced at plant K. On day D, constraint 7 denotes the capacity constraint such that the daily production node of each plant does not exceed its capacity. Constraint 8 ensures that the departure time of each job is not earlier than its production completion time. Constraint 9 calculates the arrival time of a job ij at its distribution center. Constraint 10 ensures non-splitable delivery. That is, each order can be delivered to its customer only after all its orders have been arrived at its distribution center. The objective function of minimize total cost and constraint 11 together determine the target time. Constraint 12 defines all the variables to be used in the model. Then we analyze the computational complexity and the intractability of this IPDS problem. First, we prove this problem is NP-hard, even under very special cases, such as JKL equal 1. And okay, so second, we show that no polynomial time approximation algorithm have a constant worst case bound. So we can know that this IPDS problem in our work is NP-hard and intractable. That's very difficult to be resolved. Therefore, for this very difficult problem, we have to transform our model and propose the corresponding algorithm for the transformed model. Especially, we reformulate this IPDS problem as a bi-integer linear programming model. That's BILP, BRLP model based on the setting partitioner formulation. The main idea is that any feasible schedule consists of feasible sub-schedule of all jobs. So here, feasible schedule is considered for jobs. Here, let Pij be the set of all feasible sub-schedules for job ij. Nij denotes numbers of feasible sub-schedules of job ij. And this parameter f pi ijn denotes the total cost of the nth sub-schedule for job ij. Next, I detail the process of obtaining all feasible sub-schedules and their corresponding variables and the total cost. First, for each job ij, we solve a feasible sub-schedule problem, that is the FSP problem, to generate all feasible solutions to this FSP model. And the FSP is derived from original mixed integer programming model, where the objectives are not considered. That is the FSP model. For this FPS model, we don't consider objective. Okay, such each sub-schedule of job ij is a vector. Okay, specify the job assignment xi, j, n. The projected starting time for each job t, I, j, n, s, and the delivery time to the customer t, I, j, n, s, as indicated by this formula. Once the subschedule pi I, j, n of all jobs is obtained, the optimal departure time from this manufacturing plant can be determined accordingly by solving the CFS problem. Okay, with objective of minimize total cost of job ij. Here we get in the objective function. Okay, this objective function is much simplified from compared with the original one. So, and the CFSP is also derived from this original MIP model. This CFSP model is much simpler than the original MIP model. In this way, we can have total cost and departure time of each job ij. Finally, we define a binary variable yij, yijn. Okay, yijn. Here, yijn is 1 if sub-schedule pi ijn of job ij is selected in the final solution to the IPDS solution, and 0 otherwise. Then the IPDS problem can accordingly be reformed as the following BIT model: terminal master problem. Here, the objective function 21 aims to minimize the total cost of the final schedule. Constraint 22 ensures that only one sub-schedule is selected for each job. Constraint 23 presents the capacity constraint. Constraint 24 ensures that all jobs in one order have the same delivery time to the customer. So next, we present the solution approach. So as we see, in numerous, we have numerous sub-schedules. Each sub-schedule here, each sub-schedule can consider as a column. And the constraint, there are many constraints that make the above MP problem intractable to solve. Accordingly, we propose a 2-layer column illumination, that is a CG-TLCE algorithm, to reduce the size of the column used in solving the problem. It also relaxes the constraint initially and then stabilize add then to simplify the computation. Specifically, the algorithm comprises column generation and an iterative process. Each iteration consists of 2-layer column illumination and column filtering. In detail, we first use column generation to solve the linear relaxation of the MP without constraint 24. We don't consider this constraint. By column generation, we can obtain optimal solution cost of CLMP and reduce the cost of all YIJN, the optimal sub-schedule of job ij. Here, YIJN denotes the nth schedule of the order IJ, job IJ. Secondly, as we know, the set of columns obtained by optimizing LP relation problem cannot guarantee the optimality of the integer programming. We select some additional columns with reduced cost no larger than the threshold to expand the set of columns used in the final integer problem. This threshold is proportional to the gap between an upper bound and the lower bound of the original objective value of MP problem, which is referred to the idea of column enumeration. Finally, we solve MP containing all columns in the expanded set by conventional solvers. In each iteration, we initiate set epsilon, that is the gas gap between the upper bound of the optimal cost of the MP and the linear acceleration of the MP without constraint 24. We denote as CLMP. Here, sigma and eta are given parameters, and in each iteration will first perform two-layer column enumeration, then filter column by a ruler derived from a feature of the IPDS problem, and finally solve the restricted MP problem consisting of all columns in the current set. For the two-layer column enumeration, we set UB upbound gases. In the first layer, we enumerate all columns in the CLMP whose reduced cost is no larger than upper gas minus the optimal solution cost of CLM to form CE. Consequently, we directly solve the restricted LPM, which is a linear relaxation of the RMP, consisting of all columns in the NCE. In this way, we can obtain optimal solution cost of the RLMP and reduce the cost of all columns. Then, in the second layer, we enumerate all columns in the RLMP whose reduced cost is no larger than U upbound gases minus the optimal solution cost of CLM to form NCE2. Then, based on the ruler derived from the non-splitable delivery of our IPDS problem, we filter column in NCE2 to generate NIJCF. Okay. Finally, if no feasible solution to the RMP has been found, we modify epsilon by this formula and enter the next iteration. Otherwise, the algorithm terminates here. So next, we present numerical experiments. We base our numerical experiment on real cases based instances, including real incidents derived from MTO finisher manufacturer in China, and randomly generated instances based on the real setting of this manufacturer. And this manufacturer can produce 4 types of the products and established 4 plants and 6 distribution centers across different locations. We construct 12 test instance set corresponding to each order quantity, that is I equal 10, 20, 30 until 120. And each set consists of 5 instances. To evaluate the performance of our proposed CG and the TLCE algorithm by comparing it with 4 benchmark approaches and various parameter setting. approach 1, that is column, yes, the ordinary column generation. It resolves the linear relaxation of the MP by CG and then solve the RMP consisting of all generated column. Approach 2, combine the column generation and the table search heuristic algorithm. This algorithm is proposed by a paper in JOC, Journal on Computing. It uses a table search heuristic to improve the solution generated by CG. Approach 3, that is Glooby. We use Glooby to solve the mixed IP problem. So we should notify that Glooby method could only solve small scale problem. So finally, approach 4, that's a rule-based approach. This approach is used in the practice by the MT or finisher manufacturer, and it schedules the production and distribution sequentially and separately. So we show the scheduling result of incidents through the Gantt chapter. Okay, that is a for plant. Okay, the assignment of job to the 4 plant. Okay, to the 4 plant, plant 1, plant 2, and plant 3, and plant 4. That is time scale. Okay, so starting time and finishing time. That and this is departure transportation time to dispatcher time for transportation delivery to the distribution center. Okay. So we take the total cost and the running time as a comparing measure to comparatively evaluate the various approaches. First, it is evident that the proposed CG TLCE algorithm performs well with an average gap of 0.84% in the base cases, but that of CGTS and the ReLO-based approach is 90%, 70%, 6.94%, and 23.55%. Besides, the average gap of Glooby is 0.1% larger than CGL than our algorithm, but so it is running time is too long, and is 7.44 times longer than ours. And even for large number model, it cannot generate the optimal solution. Therefore, the CG-TICE algorithm outperforms the 4 benchmarkers with respective to solution quality. Moreover, the CG-TLCE algorithm is capable of generating optimal or near operation solution. Additionally, we'll analyze the cost component of the solution generated by various approaches in the base cases. Moreover, we can derive that compared to the rule-based used by the finisher manufacturer, our proposed CG-TLCE algorithm can save 23.95% of the average total cost. Finally, we come to conclusion for this talk. So in conclusion, we investigate the integrated multiple plant quality production, inventory, and the harbor stock delivery problem of Splitable orders. We formulate this problem as an MIP problem to minimize the total cost. Our subsequent analysis of the computational complexity of the problem demonstrates that it's an NP hard problem, and there are no polynomial time heuristic for it with a constant worst case bound. That is, the problem is intractable. To solve this problem, we reformulate as a binary integer linear programming model based on the setting a set partitioner formulation. And then we propose a column generation and a two-layer column enumeration algorithm to resolve this problem. Using real data-based incidents from the MTO manufacturer, finished manufacturer, we conduct a series of numerical experiments to evaluate the performance of our algorithm by comparing it with 4 benchmark approach. Furthermore, we analyze the impact of the sample important factors and then gain some manageable insights. That's all for my talk. Thank you very much.
Well, thank you very much, Professor Jiang, for offering this impressive and very informative presentation. And actually, the topic is a very hard topic, as you mentioned, that from the different aspects, from the mathematical and also from application side, so the research on the optimal decision making in the complex supply chain network is a very hot topic. And thank you for giving us the more information about the details, what your research has been done in your group, and also what would be the future aspect of this challenging topic, because this also could be very related to the Journal of Complex Engineering System. And we hope that we could have a more good discussion with Professor Jiang, because he's one of the pioneers of this field. So now we have time for some questions. So first, I would like to ask from the panelists. So if there are any questions, so it's time to ask a few questions from Professor Jiang. Well, you can raise your hand, or you can copy paste your question in the Q&A area, and then we can try to answer your question. Okay, so meanwhile, we are waiting for some questions from the panelists. I would like to ask you maybe one question. So I'm very curious to know about the more basically the details about this optimization approach you presented. So the first question could be, so how did you look at the uncertainty? So in your constraint, for example, in this MIT, the optimization problem. So if we have some uncertainty in the order or in the task, so how this optimization will consider the uncertainty in the optimization part?
Hello, so it's not clear. Yeah, okay.
Yes, my question is about the existence of uncertainty in the optimization part. If we have some uncertainty in the time or
okay,
the order.
okay, I see. Okay, actually, this model we don't consider uncertainties. Okay, that is, so if we should consider uncertainty, we couldn't use this MIP model. That's a mixed integer model. We should have used stochastic model. You know, it's different model. Okay, that is so if there are, we consider uncertainty, the problem is much more difficult. So that is our topic for the future research topic, right?
Okay, thank you. So also about this supply chain, because in the manufacturing of the supply chain, so when you want to start to make a model, when we have for example, a specific manufacturing problem. So because when you look at the orders, maybe the order will come after some delay. But do you think also the time delay also could be one parameter we should consider in the optimization problem? Or how do you look at the delay in the order in the supply chain manufacturing?
So we have already considered delay in this in this integrated production and delivery schedule problem. So I will show you. So 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 in this model, right, the original model, right, that's the delay, okay? That's the delay. This is total delay for different so that is delay. So we'll consider delay, okay? Okay. The delay is calculated by this original model. This is okay. This is delay, okay. For the objective function, we have already considered delay. This delay is okay.
Oh, yes, thank you.
Cause delay. Okay.
Yes, exactly. So thank you very much because this topic, as you said, that from application side has a lot of interest. I hope the audiences in the webinar today. So if you have any question or any ideas, so please feel free to contact our distinguished speaker, Professor Jiang. So maybe by email, because of the time of the webinar is limited to 1 hour. So at the end, it seems there is no question, Professor Jiang, to you from the panelists. So I would like from my side and also from the editorial board of the Journal of Complex Engineering System, would like to thank you very much for offering this excellent presentation today to our audiences. And I hope all of us basically would get more ideas about this topic. And I personally are very interested in this area and would like to discuss maybe more details with you, maybe in the future. And also you are very welcome to visit our department in the Polytechnic of Milano in the future. And then we could have a more collaborative discussion. So thank you very much from my side, Professor Jiang. I know it's a bit late at your end. So
Okay, thank you very much for Professor Karmi for invitation. Right. Okay.
Thank you, and look forward to meet you in the future. And also thanks to our audiences. Now we can close the webinar today. And this has been recorded and will be available on the journal platform. Thank you and have a nice day and say goodbye to all of you. Bye.
Okay.